Hey everyone. Right, so now what we're going to do, now that we know some of the basic Python syntax, is I want to move sort of more strongly into the Houdini side. How we're going to start applying this in Houdini and what types of things we can do in Houdini, because that's going to make it more practical and it's going to start, I think, showing you, what you can do with this, and hopefully that will help solidify the information because it's a lot to take in. Now, the best way to do this is through the Houdini help browser. So, even though there's a lot of knowledge about Python, obviously just Googling general things that you want to do in Python, so anything about the general syntax there's so many resources out there, so much information just readily available. So if you're stuck with some kind of syntax, or how do I do this, how do I loop through a dictionary if you've forgotten how, it's so easy to find that answer online. And then anything specific to Houdini, the help browser is actually really good. I'm going to show you how to navigate it and what some of it sort of means, some of the more hidden information inside of it, so that it makes more sense to you. But what I basically am trying to do here is teach you how to fish instead of giving you a fish, teaching you how to navigate the different resources and build that on top of just general syntax knowledge, which will then mean you can kind of do anything and discover anything, because there are millions of different methods and modules and things that you can do with Python, and in particular within Houdini there's loads you can do. So a lot of that's going to require some self-exploration. So giving you knowledge of how to use the help browser and what it sort of means is going to be the next big step, and then after that we're going to start building on that knowledge by sort of layering up some more common use functions and methods and modules and stuff, things you're going to want to use all the time, because then that's going to form a good foundation. It'll let you get used to using the Python modules this way, and then of course you can expand that knowledge. Okay, so that's my kind of plan, my roadmap. Now, I always have a help browser on, but sort of collapsed off to the side, because I don't really like the floating one that keeps going away, whereas this I can then pop it out whenever I want, and it just sits here no matter what I click on. To find the Python package that we're looking for, you can type HOU, right? So that is the name of the Houdini Python package. And you'll see if we go down the list right to the bottom, Python scripting, there's a who, and then it says in gray on the side, package. Okay, that's what we're looking for. This is going to be your home base for building Python scripting in Houdini. Now, a package is essentially just a collection of other modules. And modules are essentially a collection of methods, which methods, I even keep calling them functions, but essentially it's a thing that does a thing. It's like an action, or a function, or in this case, they call them methods, all right? So modules contain methods, in other words, things that you can do to other objects in the scene, or sort of functions that you can run. And then there's another thing called classes, which we're going to get into more in a bit. But just know that the package can contain modules, submodules, and classes and functions, right? So who is the big one? Most of your functions are then going to start with who dot and then something, so you'll see here, and then you'll find there are submodules that you need to reference. So we're just going to start, and it'll make more sense as we go. Now, there's a really long list. Of course, it's sorted into categories, so you can sort of see these general categories over here, and you can scroll down, but you can also filter. So if you're looking for something specific, you can filter it and find that a lot easier. One of the first things I want you to be aware of when you're in the Houdini help browser is the naming. If it has lowercase letters for the very first letter, right? So the whole thing is lowercase, as opposed to having, it won't necessarily be the whole thing, but it'll be the first letter is lowercase, and then it'll be capitalized after that. But it does not have a circular brackets at the end. Then this is typically going to be a module. Okay, so like who.anim is a module, and you can see underneath it even specifically says it's a module which contains functions for working with animation utilities. Okay, so if I middle click on that, it's going to open up this other module. You'll see there it says it's a module, and it has a whole bunch of methods that we can apply. Okay, so lowercase first letter without circular brackets is a module. With circular brackets, but still also lowercase in the beginning, so you can see here like this add animation layer, that is a method. Okay, so that is something that you can actually run or apply. You can middle click on that, and it's actually going to show you how to apply it, the arguments you need, what it returns, and an explanation of what it does. Okay, and you'll see there it says a hom function. Okay, if it has a capital letter in the beginning and it doesn't have circular brackets, right? So like this, base keyframe, anim bar, these are typically going to be classes. So if I middle click there, you'll see there it says a class. Okay, now we have already discussed what a module is and a method, so basically just functions and then big collections of functions, and then including then a package, which is just a collection of modules, which is then a collection of functions. So it's essentially just this hierarchy of a way of sorting all these functions into different groups, right? But a class gets a little bit more complicated. And the best way I can think of describing a class to you guys is human beings, right? Human beings in general. Not a particular human, but just the idea or concept of a human being could be considered a class, right? So it's essentially a definition of the default that you would expect from a member of a certain species, right? So humans. And so you might find that, so with humans, you would have default information like typically humans will have 2 arms and 2 legs and 2 eyes and a nose, right? Or whatever. And there's a bunch of other, even things like a range of, heights. So someone could be, there's a range of average heights, even though you can have exceptions, incredibly tall people, incredibly short people. You can have someone that has 1 arm instead of 2. There are exceptions, but those are each instance of that class can have exceptions to it and can have unique information, right? Specific information. But the class is more of just a general definition. And you can also have subclasses, right? So think of it like there are animals, right? Animal is a class, but then under animal you can have different types of animals, one of which would be mammal. And under mammal you might have primate, and then under primate you have human. Okay, so and we as humans have certain things in common with other primates, but there will be things that chimpanzees have that we do not have. So we inherit properties from parent classes, but when it splits into 2 different classes on the same level, you might have differences between yourself and a sister class, right? So human to chimpanzee, we might have share the same parent class, which is primate, but we will not have all the same properties as them, but certainly a few in common. So that's how classes work. That's how you can think of them. Now, a class, or at least an instance of a class in Python, is an object, right? And Python is object-oriented programming. Really what that means is when we refer to an instance of a class, like in our case now, bringing it back to Houdini land, a node, right? There is nodes in general. So if I search node, there's a who.node class, which is a definition of what you can do with nodes typically. But this particular node that I have in my scene right now has certain properties. This node is called Geo1. No other node is called Geo1, but I can do things to this that I've inherited from the class of node. Okay, so if we go to that who.node class, you'll see at the top here it explains the inheritance actually as well. So it even shows us what our parent classes are that we're inheriting information from, and it even then also shows certain subclasses. And it gives us a list of methods, but these methods can be applied to members of this class. So if I have a node, these methods should be able to be applied on that node. Okay. another analogy just to make this crystal clear, it's like, let's say you've got a spoon. Well, you can scoop with a spoon and you can put the spoon in your mouth, so there are certain actions you can perform with a spoon. Now you can also scoop with a shovel, but you can't put a shovel in your mouth, right? So you can, it's like, depending on the type of object it is, it has its own list of things you can do with it, actions, right? So, but those are methods and functions. Okay. So I hope that is all making sense. So now, if we refer to this node in our scene, we should theoretically be able to do any of these methods to it. And that's where you can really get creative and figure out what the possibilities of Houdini Python are. Is you can go through these lists, like saying, okay, look, let me look at the whole list of node methods and say, what can I do with this? I can insert input. Okay, so you can change the inputs of the nodes, or you can what else can we do? We can figure out the type of node that it is. We can look at all of its children. We can figure out the name of the node. We can add another node inside of a node. Okay, so this is where it starts getting really fun, because now this is giving you basically, like I say, all the possibilities of what you can do to these particular nodes. Now, just another syntax thing, or kind of how to read the help browser properly. I want you to see that these double up arrows mean that these are methods that are inherited from a parent class. So a node lives under the who.networkMovableItem class, which itself lives under the who.networkItem class. So there are certain things you can do to all network items, then to all network movable items. So for example, sticky notes are a network movable item, but sticky notes are not nodes. You can't dive inside of a sticky note, but you can dive inside of a node. So they are different subclasses of the parent class who.networkMovableItem. Okay, and things like asking the name of the node is actually not really a node method. It is a method that belongs to the who.networkMovableItem class. Okay, because you will be able to ask the name of a bunch of other items that can be placed and moved around in your network, not just nodes. But the node subclass inherits this method from its parent, so you can apply it to all nodes. Okay, so that's sort of how it works in general. So now let's do a little example and see what we can do, because I also want to show you how to apply methods properly. So I've got a node in my scene. It also has a couple of nodes inside of it. A file node, which we cannot dive inside of. It's just a base node. We've got an attribute wrangle, and if I dive inside of that, you'll see it's a locked node, and it includes an attrib vop, an attrib wrangle core node, but it is actually just called attrib vop1. Okay, and then a rop geometry node, which again we cannot dive into. Okay, so just 3 different nodes inside of there and a geo node, right? Now, if you have your Python shell open or your Python source editor, you can drag a node inside and it will actually create a quick reference for you. So really useful when testing things on nodes, right? So if I drag it inside of here, you'll see it actually creates an expression for us, which is helping teach us how to refer to a node in Python. Now, it first references the package, and then it has a dot. Now, dot is almost like kind of opening up an item, right? So going who dot node means go into the Houdini package, so this package, and find a function or a method called node. Now, you'll see it's lowercase n. Remember, I explained that the uppercase n, like we clicked on over here, is the class. But where is the function? Over here, who dot lowercase n with circular brackets. If there was one, which I don't think there is, but if there was one that was lowercase n but with no circular brackets, that would be another module. So it would be a submodule, but that doesn't actually exist because we have a class for it instead. But this who.node function, let's have a look at it quickly. So you'll see there it's a HOM function, and it says basically given a path, then it will return a node object, and it returns none if the path does not refer to a node. This over here in the gray sort of backdrop is really vital. This is like the most important and condensed summary of what this node does. Yes, it has a nice explanation afterwards, including other examples and other sort of things you should look at, which is really cool. But this really tells you most of what you need to know, other than just maybe an explanation of what it actually does. Inside of the brackets are your arguments. In this case, we only have one argument. That could have many arguments, but they are always keyworded in this case. So they will have some kind of word that usually tries to explain what it is or wants. But if it's not very clear, they will usually explain it in the definition. In this case, it just wants a path, which is quite self-explanatory, so they don't really need to break it down for you. So it wants one argument, which is the path to the node, and then this little arrow is telling us what it's going to return. Keep that in mind because not every method actually returns something. So if it doesn't return something and you try to store it in a variable, then it's going to just return none. However, things that do return something can also sometimes return none, depending on what you've given it. So in this case, if you give it a path that does not actually exist, there is no node that lives at that path, then it's going to return none. So it'll say here, returns none if the path does not refer to a node. Okay. But assuming it does find a node, it is then going to return a who.op node, right? Now you'll see it's a hyperlink. That's really quite cool that it puts it as a hyperlink for us, because it helps us kind of dive down that rabbit hole of saying, okay, we're going to run this function, which then returns this an instance of this class. So now we can go to this class and see what else we can do with it. All right. In this case, it also happens to be another node, but it's specifically an op node, which is interesting, right? So it's a subclass. If we middle click, we can see what it is, right? It's a subclass of who.node. Okay. So in this case, it's basically saying it's not going to just return an instance of who.node. It's specifically going to be an operator node. So probably that function cannot be run on things that are not operators is basically what it's saying, right? And again, this shows us its parents, which includes who.node, and it shows us its potential children. And then an explanation of what this is, okay? As well as then methods that can be applied to that, okay? So when we get the op node reference, all of these methods can be applied to it. Okay, so this is basically telling us what it gives us, telling us what it needs, and how to write it. Okay, so now we can run this. Now we need to store this in a variable, because otherwise we're going to have to run the function again. So if I say n equals and then who.node and then that, now you'll see it's just stored to the variable. Let's just set it. So if I now go n and then hit enter, it then calls that that variable, right? And what it has printed for me is a special object. Like basically when we see these triangular brackets, it's saying that this is an object, right? So it is an instance of a class. So you can think of this, sorry, I like to think of this almost like packed geometry, right? So I'm trying to put this in Houdini terms. It's like packed geometry where it's a compound object. So on the top level, it may look simple. It's got just a point and a primitive and a vertex, and it's just one packed object. But if you open that up, there might be tons of points in there and loads of attributes that are not visible from the top level. So this is merely a reference to the node. Okay, it is not just, this is not a string. Sorry, man, I keep clicking on it. This is not a string, even though it's printed some text. This is just a representative sort of label on the top level of something that is a much more dynamic object that can be opened up and actually have things applied to it. And what it can have applied to it is this whole list of methods, right? So if we have a who.obj node, which is saying it's basically an instance of this class of type geo, so there's also a type to one of these instances. So that's a property of that class, and then it lives at this path. Now, how it prints this information is every class has a kind of almost a property that defines how it should print. So if you want to print it, because it's obviously this dynamic object, how does it print all of its information? So it just summarizes it by telling us what instance it is, what type it is, and what the path is. But really, we can get more information from this by running these methods. Okay, and that's what we're going to do. So because it is object oriented, if we refer to our instance of this class and put dot, it is then accessing all of the modules, the methods that are applicable to that particular object. Okay, and because the object is of a type op node, it means that everything in this list we can access. So now we can go through this list and see what we would like to do. Now there is something that I want to do I'm going to show you as an example things that we've inherited from who.node. One thing I want to show you is all sub children. This is the one I'm after. Okay. Now I wanted to show you this example because it kind of does some cool and interesting things. This is also a very commonly used expression. You'll use this quite often in building tools. But it has something very interesting here. The arguments have defaults, right? And what that means is that basically every argument has a default value, therefore it's kind of optional whether or not you actually give it the information that it's asking for. And if you choose not to, then it will just assume this value. So this handler has 3 arguments, but all of them actually have defaults. So you could run the all sub children function with no arguments in it, and it will actually still do something. Okay, and what this is doing is returning, so let's see what it says. It returns a tuple. Again, remember, going back, I said a lot of functions are going to return tuples if it needs to give you more information. Well, here's a tuple of who.node. So these are instances of a who.node type class, all stored inside of a tuple. And you can see here, I mean, every triangular bracket basically shows that's one item. So we've got there's our file node, there's our wrangle. Now inside of the wrangle is also that attrib vop, right? Even though the wrangle is locked, so that's important to note. And then there is also our rop geometry node. Okay, so it's returned 4 items. Now these arguments, because they have keywords, if we want to start filling information for them, we have to enter the keyword to tell it what those values are, or we have to fill in all of the values in order. But if we fill in the keyword, what it does let us do is skip certain ones. So let's say we want to leave top down as true, but we want to set recurse in locked nodes to be false. We don't have to necessarily enter this one and then that one. We can simply enter the keyword. So let me just sort of explain what I mean. All right, if I all sub children, if we basically want to set recurse in locked nodes to be false, which what that does is saying, should it look inside of locked nodes? And our wrangle is a locked node, so basically the reason it's returning this attrib vop reference here is because it's allowed to look inside the locked nodes. This is set to true. But what if I want to set it to false? So all I get are my 3 top level nodes. It will go inside of, if I had a subnet, it'll go inside because it's not locked, but it will no longer go inside of these locked nodes. Now if I want to do that, and I just say here false, how does it know that I'm referring to this being false? Because this is also a true false value that it's looking for. So if it doesn't know what you're referring to, it's going to assume you mean it in the right index order, which means if I put false, it's going to set top down to be equal to false. Okay, and top down is basically just saying, should it list, what order should it list it in, basically, when it finds the wrangle and then the attrib vop1 inside of, so the wrangle core inside of the wrangle, you'll see that wrangle is listed first and then its children are listed second. Top down being false would do it the other way. You would have your children first and then your parents second. So if I just enter false, it's going to assume that I mean that top down should be equal to false. Okay, so there we go. If I do that, it's now doing it the other way around. There's our wrangle core and then there's our wrangle, right? That's not what I wanted. I want to specifically say that false should be recurse in locked nodes. So one way of doing that is that we have to first go and enter true for top down so that the second argument can be set to false. Okay, and then I can ignore the third argument because I don't want to change it. Right now you'll see here it's only listing 3 items. Right, so our file, the wrangle, and the ROP, but no attrib core over there. Right, so that's the result I wanted, but I had to enter the word true first in order to basically tell it that I want to change the value of the second argument. And this is kind of confusing and a waste of space, right? If I know I want to skip ahead to just the second argument because it's got a keyword, I can just say recurse in locked nodes equals false. Okay, and now when I run it, because it doesn't have a top-down value, it takes the default of true, and it specifically sets that value to be false because it matches this keyword. Okay, now I know that was a lot more to type than having to type true and then false, but this is easier to read in your code now because it becomes obvious now what value you're changing. Whereas if you just have that where it just says true, false, false, true, whatever, like you can have a whole bunch of arguments. It's very confusing to read. So really important to understand that you can refer to these using their keywords. But do keep in mind that any arguments that you have that do not have an equals, so like here this set selected method has on, and then clear all selected equals false, that on function, argument is mandatory. You must specify on being either true or false, right? And you can do it out of order if you refer to the keywords. So you can say clear all selected equals true, comma, on equals, and then you can give it a value. So you can do it out of order, that's fine. But you cannot not have a value for on, otherwise it will just error out. Okay, so keep in mind whether or not things have defaults or not, and then also what they return and the keywords so that you can override only the things that you want to override. Okay, now what this has returned is a list of nodes inside of our node, right? And to just show you how we sort of work with Python typically is I've now created a reference to my node. I can now go n.allSubChildren and then recurse in locked nodes equals false, but store this as maybe C. So that's all my children are stored in a variable called C. So now C is equal to a tuple that is a list of, well, you know, not a list, sorry, a tuple of my 3 different nodes. Well, now I can loop through that list. So I can say for, I'll just call it for child in C, right? So I'm looping through my list, my tuple, where I'm giving it the variable child for every item in that list. And now what I can do is print child, which then if I hit enter, you'll see it's going to print file1, attrib1, and then rop1. Okay, because when we print a node, it actually prints not like this object reference. It just actually prints the name. So you can see there now it's a little easier to read. Okay, obviously we can do that. This is actually kind of cumbersome to do in the Python shell, but we can do it in here as well. So we can do this, drag that in, n equals, n c equals n dot all subchildren. I'm just going to not put the optional arguments, so I'll get all 4 nodes, and then what I can do is say for child in C print, and maybe we should say C dot path. There's another function called path which will give us the path to that node. So now what you can do is not C, child dot path. So inside of the loop, it's going to refer to the child, which is each item in the list one at a time, say dot path. Now how I know we can do that is because I've gone and looked at who.node. No, not that type, this here, the class, and you can see there is a method called path, which is inherited from the who.network movable item. It has no arguments, it just returns the path, so it returns a string, which is the path to that node. And now if I say apply, I'm actually glad this happened, by the way. I want to show you a bit of a gotcha. In the Python source editor, it's a little bit finicky. If it fails, if it errors in certain ways, not every way, but in some ways, if it has an error, particularly a Houdini type of error, then it seems to lose reference to the Houdini module. The whole module seems, well, the whole package it seems to lose reference to, which is really annoying. So we just need to put a line of code to re-import that package right at the beginning of our code, so no matter whether it has errored the last time, when we click apply again, it's just going to re-import that package. Now, I haven't talked about importing, but that's really good to bring up right now. Packages, which are just a collection of modules and classes, and then modules themselves, can all be imported into Python, right? So some sort of collections of functions do not inherently live in Python, like the maths function, for example. There's a whole module of math functions that is not just default in Python, but if you just type import math, then you now have access to that math module. So it's sort of living there, but it's just not loaded, right? It's not imported. And in this case, we need to import who. So whenever I start typing in a Python source editor, the first line I'll put is import who. Not because you usually have to do it, because it should have who by default, but because if it errors with a Houdini specific error, it loses that reference to it. Now it will work again, okay? So there wasn't anything actually wrong with my code. Now it was the fact that before, when I clicked apply, it actually broke, and then it loses the reference. So now you'll see it creates that list and then loops through the list and prints child.path. So now I get a path to my file node, a path to the attrib wrangle, a path to the attrib core, and a path to the ROP geometry. Okay, so I know that's quite a lot to take in, but I hope this has been a good crash course for you into basically how to use this help browser, what some of these things mean, like arguments, what it returns, subtypes, class inheritance, modules, methods, optional arguments versus mandatory ones, and then kind of how to work in this sort of object-oriented way where we, we have one type of object and then we run a method which returns another type of object which we can then do other things to, and so it's this kind of like, rabbit hole really. Python is a total rabbit hole. Okay, so I'll see you guys in the next lesson. Now that we know how to do all of this, next time what we're going to talk about is some common things that we can do with nodes and parameters. So we're going to start diving deeper into Houdini specific things.